Our first speaker this afternoon is Matthew Kroeker, and he is going to be talking about average hyperplane size and complex representable matroids. Thanks, Matt.
Thank you. Great, the mic's on, sorry. Let me make sure this is working. Great. Okay, thank you to the organizers of this conference for allowing me to speak. I'm always a bit self-conscious speaking after my supervisor, Jim, especially today because you can see that I just completely ripped off his style of making slides. He really came up with this kind of color scheme, but I thought it looked nice, and I just didn't realize I'd be going right after him, so it's kind of obvious. Thank you. Yeah, imitation is the sincerest form of flattery, he said. Yeah, exactly. Right, so I'm going to be talking about a project that'll be part of my PhD thesis. So it's, of course, a joint with my supervisor, Jim, and also with Rutger, as well as Ben Lund, both of whom work here at IBS and whom I've had the great privilege of visiting a couple times now to work on this project. And so in my opinion, the whole story behind what I'm talking about today, really begins with something called the Sylvester-Gallai theorem. This is kind of a nice theorem in discrete geometry, which says in matroidal language that if you're rank 3 real representable, then you have a 2-point line. And the sort of theme of the research for my thesis had been to kind of try and prove higher rank analogs of this result, higher rank Sylvester-Gallai type theorems. So for instance, if we bump the rank up to 4, when can I guarantee the existence of a plane that has exactly 3 points? That's an example of the type of problem we were interested in, and so on to higher dimensions too. And at some point we came across a stronger result. This is due to Melchior, and it says that if you're rank 3 real representable, then the average number of points in a line is strictly less than 3. Okay, so that implies Sylvester-Gallai. And the bound of 3 is also best possible. So for example, you can look at this family of matroids here, which we call the near pencil, and see that the average is tending to 3 as you go up in size. So I think this is a really nice theorem, and Jim and I were quite struck by it. It's very sort of easy to state, and I also think that it's kind of surprising. You know, real representable matroids can be fairly wild, but yeah, I don't think it's exactly an obvious theorem, but it has a really short and beautiful proof, which I'm going to briefly advertise just because I like telling it to people, not because it has anything to do with the rest of the talk. But what you do to prove this is, you take a representation of your matroid, so you have this representation which you can view as sitting in the projective plane. And because you're in the projective plane, you can dualize, or apply projective duality, I mean. So rather than considering an arrangement of points in the plane, you consider an arrangement of lines in the plane. So something visually that is kind of like this. You have this arrangement of lines which correspond dually to the points of your represented matroid. And when you look at the intersection points in this line arrangement and view them as vertices, what you see is that you're dealing with a graph embedded in the projective plane. So by Euler's formula, this graph has average degree strictly less than 6. And when you take that information and translate it back into the original problem, you get Melchior's theorem. So it's this really beautiful application of kind of classic graph theory to obtain this kind of nice and kind of non-obvious result. But like I say, you know, Jim and I came across this theorem of Melchior, and we were interested in it, and in keeping with the sort of theme of our research, we asked ourselves, well, what about higher rank flats? So again, if we just go up to rank 4, is the average size of a plane at most an absolute constant? And the short answer is no. The construction is nothing exotic. You just take a direct sum of 2 lines. Okay? And the reason this is a counterexample is that every plane in this matroid has to look like this. Every plane is forced to contain one of these 2 lines. So because these lines could be arbitrarily large, there's no hope of bounding. You just can't bound the average plane size in this case. But the nice thing about this this rank 4 question is that, you know, rank 4 is reasonably intuitive, and you can kind of just think about these rank 4 matroids, and you stare at this construction, and the conjecture you eventually arrive at is that this is essentially the only thing that can go wrong. And this is something that we proved last year. So this is a result with Rutger and Jim, which kind of says exactly what I just said. If you're rank 4 real representable, and you're not the direct sum of 2 lines, then the average size of a plane is bounded by an absolute constant. And I'm going to kind of go through how we proved this. It took quite a bit of time and effort to figure out, but I think I can still really give you the whole idea of what we did in this talk. So at first, what we thought was that maybe we could take Melchior's approach and, you know, dualize so that we're considering a hyperplane arrangement, and then maybe tease out the bound in some way using the Euler-Poincare formula. That didn't seem to work. So for us, the sort of natural first step was to come up with a new proof of Melchior's theorem, which we could hopefully generalize. Okay, so, and when I say Melchior's theorem, I don't mean with this best possible bound of 3, just I'd be happy with any bound. I just want a proof technique that hopefully extends more naturally to higher rank. Okay, so what gave us the idea that we could get another proof of Melchior's theorem was this theorem of Joseph Beck from 1983. So Beck's theorem is a fairly classic result in discrete geometry. And what it's saying in matroid language is, well, it's an approximation on the number of lines in your matroid. And it's a good approximation on the number of lines. So what you do is you take your matroid, say that it's on n points, and you take a largest line in your matroid, call it x. Then the number of lines in your matroid is approximately n times n minus the size of x. And I've written omega here, but it's really easy to check that this is a best possible bound. So this really is a good approximation on the number of lines. Yeah, incidentally, I forgot to make the disclaimer I planned to make, which is that you can assume that any matroid I'm talking about is simple. Okay, that's important. And so when I talk about the size of a largest line, I mean number of points, number of elements. You can just assume that I'm talking about a simple matroid if you like. Right, so Beck's theorem is this good approximation, but this really gets us halfway to Melchior's theorem. Because if you want to bound the average size of a line in your matroid, this is equivalent to showing that the total number of lines in your matroid and the aggregate size of all the lines in your matroid are within a constant multiple of each other. Okay, so if you have this good approximation on the number of lines, that gets you halfway. right? So basically what I've just said is that now we want to show that the aggregate size of the lines is also approximated by this quantity. So when I write script L of M, I mean the collection of lines in your matroid M. I'll use script P of M for the collection of planes similarly. So I want to show that when I sum over all the sizes of lines in the matroid, we get this approximation. And this is a pretty straightforward just combinatorial proof that only relies on the fact that a distinct pair of points in a matroid spans a unique line. That's it. So to show you what I mean, you just want to have this picture of your matroid in mind where you've picked this largest line x, and then you have this set of leftover points lying outside of it. Now for any line except x itself, it's going to intersect x in at most one point. So say we're considering some line L on t plus 1 points. So if this line has size t plus 1, then very naturally I can pick out at least t ordered pairs, the second of which is not in the line x. Okay. And because distinct points span a unique line, when I count pairs this way, I'm not going to do any double counting. So that's the proof. So like I said, these two things together give us Melchior's theorem. And to prove the theorem about planes, I'm going to take this sort of broad proof idea and just generalize it, okay? So we're going to start by getting a good approximation on the number of planes, and then we're going to show that the aggregate plane size can also be approximated in that way. All right. So it took some time to figure out how to do this, but for us the light bulb really went off when we came across this theorem due to someone named Tao Da, who was a PhD student at MIT when she proved this. And well, I've written Da's theorem for planes, but actually what she proved is for hyperplanes of any rank, but I'm just going to talk about the planes case. I have a typo right there, so that says rank 3 real representable matroid. I mean rank 4. Okay, so we take a rank 4 real representable matroid. What the theorem says is that for any epsilon I like, either a 1 minus epsilon fraction of my points are either contained in a plane or the union of two skew lines, or I get on the order of n cubed planes. And we're going to use this in order to derive an approximation on the number of planes that's kind of in the same spirit as Beck's theorem as formulated on the previous slide. So I'll tell you what this approximation is. So, right, with Beck's theorem, we're counting the total number of lines in terms of a largest line in the matroid. What we're going to do here is first pick out a largest subset of the ground set that's contained either in a plane or the union of two lines. And then we'll call that x3. And then after we've chosen x3, we're going to take a largest line sitting in the restriction to x3, and we'll call that x2. And then we get this approximation on the number of planes that, like I say, is kind of in the same spirit as Beck's theorem. So I'll show you how we derive this from Da's theorem. This Da's theorem really, like I say, the light bulb kind of went off when we saw this particularly because the theorem deals with the structure of a large plane or a large set in the union of two skew lines, right? When we saw, that's kind of the exact structure that we're forbidding, so when we saw that showing up, we really gained some confidence we were on the right track. So I'll show you how, I'll give you a sketch of how how we derive this. Actually, right, so what you want to notice is that right off the hop, Dawes' theorem gives you an incredible amount of structure. Okay? What it tells you is that you can just assume for whatever epsilon you like that a 1 minus epsilon fraction of your points are either coplanar or in the union of two lines, because otherwise we win. That's what the theorem says. Right, so we have a huge degenerate set. I'm going to call that a degenerate set if it's coplanar or in the union of two lines. So that's two cases to consider. The case that the set is coplanar happens to be the easier case to consider, so let's talk about what happens when we have the two skew lines. So this is a picture of my matroid. I have this massive degenerate set, which I've depicted in red, that's sitting in these two skew lines. And then I have a fractionally tiny set of leftover elements that I've drawn in purple. And the whole key to proving the result is to reduce to the rank 3 case, apply Beck's theorem, and then lift things back up. But there's a right way to do this, and the right way to reduce to rank 3 is by principal truncation. So principal truncation of the line x2, if you don't remember what principal truncation means, you can think of it as taking a generic projection from a point in x2, and we end up with this rank 3 matroid where x2 gets mapped to a point, and everything else in the original matroid kind of gets mapped in a nice way from the perspective of x2. And the reason principal truncation works so nicely here is that it's really well behaved with respect to this degenerate structure. In particular, because I picked x3 to be this largest degenerate set, when I principally truncate the line x2, x3 minus x2 is going to be a largest line in that principal truncation. Okay, that's not immediate or anything, but that's true. That's why principal truncation is the right thing to do here. But because x3 minus x2 is a largest line, we can apply Beck's theorem, and we get a count on the number of lines in this projection that's starting to really resemble what we're after. Okay, so we've got all these lines. I've drawn a few of them, but we have a lot of lines in this rank 3 matroid, and moreover, most of them are going to miss x2. x2 is just a single point, so most of the lines are not going to contain it. And that's really important because in the principal truncation, the lines that miss x2 all lift to lines which are skew to x2 in the original matroid. So now we've counted up a lot of lines that are skew to x2. And to finish the proof, you can see we're close. Remember that x2 is really large. In particular, it's linear in n. So generically, generically you kind of go through each of these skew lines and then you count up their spans with points in x2. That would give you the count that you want, but the problem is you need to avoid double counting. You can double count planes when you just do what I just said kind of generically. But this is where it's really important to use Dawes' theorem, in particular the fact that the set of leftovers is really tiny and x2 is really, really large. When you go through each of these skew lines, say this purple one that I've drawn here, because x2 is so large, most of these planes are going to consist only of the purple line that you chose and the red point in x2. And when you count only those ones, you're not going to do any double counting. I've swept a couple details under the rug when I say that, but this really is kind of the broad strokes of how this theorem's proved. This is really the whole proof. Right, so that proves the approximation on the number of planes, and then just like with lines, the next step is to just show that the aggregate plane size is also approximated by this quantity. And I don't have time to go through this part, but the argument here is really sort of just a slightly more intricate version of the combinatorial argument I showed you for lines. Okay, so that's how we prove the theorem about planes. And with my last few minutes, I'm going to talk about the problem in higher dimensions. So we know that average line size is bounded, and I've shown you that for plane size, really only one thing can go wrong. The problem with higher dimensions, as you might imagine, is that many more things can go wrong. With planes, it's just this two skew lines thing that you have to forbid, but in arbitrary dimension, many more things can go wrong, and it's kind of like, how do you reckon with this? Fortunately, there's a fairly well-studied notion of degeneracy that gave us a lot of insight. Okay, so this might look a bit unintuitive at first. This was introduced independently by Lovaas, Ben, and Daejeon. We call a matroid K-degenerate if it can be covered by a collection of flats, each with rank at least 2, whose dimensions sum to less than K. And what I'll tell you is that a matroid's 2-degenerate if and only if it's a line, and a matroid is 3-degenerate if and only if it's a plane or the union of 2 lines. So optimistically, you might expect, or you might hope, that if you forbid K-degeneracy, then you can absolutely bound the average size of a rank K flat in your matroid. But this is not true. This is what we had thought, at least we had tried to prove it, but things were going wrong. And eventually, Jim came up with this construction. You start with MK4, and then you iteratively two-sum lines of arbitrary size onto these bottom points here. So you end up with something rank 6, but you can check that this is not 5-degenerate. The problem is that every hyperplane in this matroid is going to contain one of those long lines. So just like what we saw with the 2 skew lines example, the average hyperplane size here can be arbitrarily large, but it's not degenerate. So I found this a bit bewildering, and we really wanted to kind of know what was going on here. It felt like somehow with all these constructions we came up with, we were close to being degenerate. And it turns out what you want to think about is just kind of isolate what goes wrong with degeneracy. Think about what makes degeneracy bad. So let me show you what I mean. Let's say we're K-degenerate, so we have this collection of flats covering our matroid whose dimensions sum to less than K. Now if I take a hyperplane, by the pigeonhole principle, the hyperplane's forced to span one of these covering flats. Okay? But because any of these T flats could be arbitrarily large, we have the same sort of problem going on that we've just talked about. So the idea is to, if you want to bound average hyperplane size, don't forbid degeneracy as I've defined it here, but just forbid the existence of some small collection of flats such that every hyperplane contains one of them. That seems to be the thing that's always going wrong, so we're going to just forbid this type of thing from happening. From what I've shown you here, this is kind of a necessary thing that you want to forbid if you want to bound the average hyperplane size. And very recently, we managed to show that it's also sufficient. So this is a theorem with Kroeker and Ben, which kind of says what I just told you. If your rank are real representable, then either the average hyperplane size is absolutely bounded, or you have this small collection of flats, which you might as well assume are lines, such that every hyperplane contains one of them. And looks like my time's up, so I'll stop there, and thank you for your attention.
I think we've got time for one quick question.
Sorry, I didn't hear you.
Could you highlight the moments in the proof where you use the representability most of all?
The representability is used just to invoke Beck's theorem. Okay, that's where you need representability. And that reminds me really quickly of just something I forgot to mention. I've given this talk a few times now, and sometimes I title it about complex representable matroids, and then I talk about real representable matroids. The results extend to the complex representable matroids because that Beck's theorem happens to hold for complex representable matroids, and that's our base case. But that is not our doing. We just did matroid theory with that as a base case, and Toth and Zoll independently proved Beck's theorem for complex, so that's why we get it. I'm sorry. I can't hear.
So apparently a affine plane over the field of order 3 is representable on CP2, right? It's embeddable.
I don't, I'm not sure I understand your question.
Oh, okay.
Okay.
The comment was that you have the ternary affine plane is complex representable.
Yes, yeah, the constants are different. I'm sorry. Yeah.
No, there are further questions, but we came back a little bit late from lunch, so maybe we'll just save other questions for the coffee break, if that's okay.
Of course.
Let's thank our speaker again.